All right, so today's notes are on compounding interest. Our content objective is to solve problems involving compounding interest and continually compounding interest, and our language objective is to use correct terminology to define variables in compounding interest problems. So first thing, what is compounding interest? So compounding interest is when interest is calculated on a principal value and additional interest that's been added into the account. So basically when you're earning interest off of your interest. So instead of just making interest on what you initially invested, they add in that interest to your balance and then or to your account, and then you continue to make interest off of the interest that they've added in there for you. This is speaking in terms of a bank. If you were earning interest, it could work the reverse way. If you were borrowing money from, say, a credit card company, they could be charging you interest off of the interest that they've added into your account. So it works both ways. So you can either earn interest off of your interest or have to pay interest off of your interest, depending on if you are loaning or borrowing the money. But compounding interest is important because this is related to our exponential models that we talked about earlier this unit. So our compounding interest formula is A equals P times 1 plus R over N to the power of NT. And you may notice this is more or less identical to our growth and decay or growth formula. The only thing is we're using P instead of a lowercase a because we're talking about the principal amount, which is a finance term when the principal amount. And then we have N that's also now included in this formula. So N is the number of compounding periods per year, or usually per year. It can also be in different intervals of time depending on the context. But N, basically what that's saying is how often they're adding your interest into your account. So if they're adding it weekly, your N would be 52. So it's going to calculate how many times you're adding in that interest into your account. So A is the final amount, P is the principal or the initial amount, R is the rate, T is the time, and N is the number of compounding periods per year. But this is our compounding interest formula that we're going to be working with. So in this first example that I have for us, I have invested $2,000 in an account that pays 3.5% interest compounded quarterly for 5 years. How much money is in the account at the end, or how much is the account worth at the end of those 5 years? So what I'm going to do is define my variables. So my A is what I'm trying to solve for. My P, my principal amount is 2,000. My R, or the rate, is 3.5%, but I need to write that in decimal form. So remember, you always need to rewrite your percents as decimals. So it's actually going to be 0.035. My time is going to be 5 years. And the N value is going to be quarterly. So quarterly is once or 4 times a year. And I'll define some of those compounding periods on the next page in just a second, but I want to go through this example first. So now I'm just substituting into my problem. So I have A equals 2,000 times 1 plus 0.035 over 4, the power of 4 times 5. So again, all I did was substitute into my compounding interest formula, and now I'm going to calculate it out. So I get A equals 2,000 times 1.00875. And I did this in my calculator. Sorry, I don't have a scientific calculator with me. I can't show you how to plug this in, but we can go over that in class together. And then I'm going to raise this to the 20th power and multiply it by 20. One thing I want to tell you guys is do not round your answers in your calculator as you go. You want to have as precise a decimal as possible. So don't write your answer and then retype it in the calculator. You want to keep your answers in the calculator as you go. So I get A equals approximately 2,380.6795, so that would keep going. When I round this to 2 decimal places, I get $2,380.68. So at the end of 5 years, I'll have made $380.68 on my initial 2,000 if I invest in that account. So if I invest 2,000 for 5 years with this interest rate, I'll be doing well at the end. All right, so I'm going to flip the page because I want to talk about compounding periods. So I've been working, or I want to show you what I mean by compounding periods, or how you can determine the end value based on the compounding periods. I'm going to flip the page. So compounding periods, these are per year. So again, this could vary if you were not working in years, if you're working in another interval of time. But for most of the problems we're going to encounter, we'll be working with years. So I'm going to define these based on years. So annually is 1 time per year. Semi or biannually is 2 times. This is somewhat confusing because these can also be every other year, but for what we're going to be doing, let's assume it means 2 times a year. But again, semi and biannually can be tricky because it can mean either twice a year or every other year. We'll assume it's 2 times per year. Quarterly, as we said before, is 4 times a year, so once a quarter, once every 3 months. Monthly is 12 times a year. There's 12 months in a year. Weekly, 52 times because there's 52 weeks in a year. Daily, 365, or if you're being really precise, 365.5. Got to account for those leap years. And then continuously is where we run into a tricky scenario. So continuously, I can't plug in an infinite value for n. So I can't plug in infinity for n and get a value. So if you were continuously adding in the interest, like nonstop interest is being accrued on interest constantly, then it would be continuously compounded. And that actually has its own formula using the number e. So our last formula we're going to talk about is continuously compounding interest formula, which is a equals p times e to the power of rt, or a equals per. So p, one thing I need you to remember though is the r and the t are in the exponent. These variables all mean the same thing. So a, p, r, and t are all the same variables as our last problem. Notice the only variable that's missing from our last problem is n. So that's because we're replacing n with our e value, which is because it's continuously compounded. So e is actually a number like pi that is irrational. So it has a never-ending non-repeating decimal. So it's 2.71828818, and it continues on. No pattern to it, just irrational. It has its own button on your calculator because it is a very important number for continually, if something is continually building off of itself, not necessarily with interest, it can also be used for population growth. So it's not like you compound population every day or once a month. So for oftentimes for population growth and bacterial growth and those sorts of things, you'll use continuously compounding. It's called the natural base. So E is called your natural base, and that will come up again when we learn about our natural logs. So E is our natural base. If you want to see how it's derived, so it's actually derived based on our previous compounding interest formula. There's an interesting proof of it or derivation of it on Khan Academy, and I can direct that to you or post it on Schoology so you can check that out. But for today, since we're trying to keep these notes short and sweet, I'm going to show you an example of using this formula for a compounding interest problem or continuously compounding interest problem to see how it works. Actually, last thing before I delve into that is one thing I want to point out that you only use this formula when it is continuously compounded. If it's using any of these other compounding interest or n values, any other intervals of time, then you're going to be using the other compounding interest formula. It's only when you're compounding continuously that you use this formula. Otherwise, you're using the first one. All right, so let's dive into this example. I say Cam invests $2,000 at 3.5% interest compounded continuously for 5 years. How much money is the account after 5 years? So this is a very similar problem to our last one. Just now, instead of compounded quarterly, it's compounded continuously. So let's try this out. I am trying to find my A value, so that's my unknown value. My principal is $2,000. My rate is 3.5%, which we know is 0.035 in decimal form. And then my time is going to be 5 years. So I'm going to plug this into my equation. I have A equals 2,000 times E to the power of 0.035 times 5. So remember, those are all in the exponent, the decimal times 5. When I calculate that out, I can plug it all in my calculator at once. So I do e to this power times 2,000. I don't want to round anything. I want to keep it as unrounded as possible in my calculator. And I get A is about 2,382.4924, so on and so forth. Which when I round that to 2 decimal places, since we're working with money, I'm rounding to cents, I'm going to have $2,382.49. So Cam would have $2,382.49 at the end of the 5 years. So that's it for today. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.